All right, tonight what we're going to be talking about is the intro topic to naming. So we're also knowing the naming unit as nomenclature. That's the more formal term for how to name a compound in chemistry. And it all depends on what type of bonds or what type of compound these various elements make together to say how you then name it. So for example, if you're sharing the electrons, if you're giving the electrons, if you're an acid, meaning you have a hydrogen, if you're an organic compound, meaning you have these hydrocarbons, it all depends on what elements are involved and how they're interacting to identify how do you name these various compounds. So the first introductory unit will be over why do they form different compounds, ionic and covalent compounds, as we'll talk about. So the first thing you need to understand is why does something become an ion? An ion occurs when some atom, gains or loses an electron, okay? And why does it gain or lose? Well, it's all because of these valence electrons. So remember that they are the outermost electron. They're in the outermost energy shell. They are the ones that are involved in the bonds. And these guys on the outer electron shell or energy level are going to be the ones that you gain or lose. If you tend to lose them, you tend to be a metal, and that's all because of how many valence electrons that you have. And when you lose an electron, you become a positive ion. So cations are positively charged. An anion, on the other hand, comes when you gain electrons. And kind of counterintuitive, but when you gain an electron, you actually are negative. It makes sense logically when you think about it because electrons are negative and you're gaining something that's negative, so that's why you are negative. But it tends to be confuse students because you're gaining something and yet you're negative. These tend to be nonmetals, and once again, as a review, it is an anion, so a negative ion. So ions are either positive or negative, depending on whether they gain or lose those electrons. And we're going to be talking about these transition metals. They are very special, but that's going to be more emphasized during the ionic naming video. All right, so bonding. Why do things bond the different ways that they do? And that, once again, all becomes is all a result of these valence electrons. Everything in the same group or family has the same number of valence electrons, and because of that, they react the same way or very similar ways. Remember that the max number is 8, and that is because that is due to your octet rule, which means that everybody either wants 8 or those 0 so that they can be like the nearest noble gas. The only exception to this rule, as we've already talked about, is helium and hydrogen, which actually want a duet. So they want a full electron shell. It just happens to not be 8. It tends to be 2. All right, so a Lewis dot structure is new to you guys. The other 2 slides were all review. The Lewis dot structure is a visual representation of your valence electrons. And basically what you do is you use your element symbol and dots to represent it. So what I'm going to do is I'm going to show, like, let's say nitrogen. So nitrogen, we've got nitrogen. How you do is you kind of pretend that it has like 4 sides. It's surrounded by 4 sides. Each side can hold up to, let's say, 2. It's not let's say, it is 2, which means that you have a total amount of 8 electrons that you can use at any time. Okay, how do you fill these up? Okay, it goes back to the Aufbau principle and the Hund's rule and all that other stuff. So what you're going to do is each dot represents a valence electron. So nitrogen has 5 valence electrons. Okay, I'm going to start at the top, but it really doesn't matter. So what you're going to do is you're going to fill up 1 electron on each side, and then when you use up all 4, now you're going to start partnering up. It doesn't matter which one you partner up, whether it's, I guess if you want to do directional, the north, the east, the south, the west. I just tend to keep going in that counterclockwise position. So if I used 4 already, I'm going to start partnering up there, which means that it's 5 valence electrons. Another way to show this, which is not known as the Lewis dot structure or Lewis dot drawings, it's more of the structural drawings, is where anytime you have these this is called a lone pair. Anytime you have a lone pair of electrons, which means 2 electrons by themselves, you can actually draw a line for it instead of having 2 dots. So I do 1 line and 3 lone electrons. These are known as lone electrons. So this is how you draw a Lewis dot. Okay? So cation examples. Let's try these. So lithium. Lithium's Lewis dot, it has 1 valence electron, so it would only have 1 dot on the top. Or you could draw it like lithium where it has a dot on the side. Okay, magnesium has 2, so we're going to have 1 on the top, 1 on the side. And boron has 3, so 1 on the top, side, and bottom. Notice I'm not partnering any of these up. What I'm going to draw now are these other holes that it could fill or possibly. So here's 1, 2, 3. Remember, everybody can fill all of these holes on the side to make it completely have its 8. Well, instead, what lithium's going to want to do is it's going to want to lose that 1 electron, so it makes it have basically all holes. Okay, so because it only has 1 valence electron, it can either gain 7 or lose that 1. It's going to choose to lose 1. So what you do is once you show it losing the 1, you put it in brackets and give it its charge of +1. You can write plus or +1. Magnesium has the choice to fill either these 6 holes that are kind of like invisibly on the sides, or what it could do is lose all of those and lose its 2 electrons. So what it's going to do is either gain 6 or lose 2. It's going to choose to lose 2. So you would put magnesium, brackets, and plus the 2. Okay, because it lost those 2 electrons. So you show in the brackets how many it currently has. Well, magnesium currently has 0 valence electrons because it lost those 2. So that's why you put brackets on it telling everybody else, hey, it had these 2 and it lost them. So now it has 0. Boron would choose to lose 3, so you'd be B with brackets and then a +3 charge. Anions. So as we've already talked about, nitrogen has 5. Okay, so 5 valence electrons, so it looks like that. So it could either gain 3 or lose those 5s. It is going to choose to lose 5. So what you do is you put it in brackets, showing that it's not the original nitrogen, it's changed somehow. Give it how many electrons it would have at the time it gained 3. So it would be 2, 4, 6, 8, because it had 5, now it has 8. Put brackets around it, give it its charge. Oxygen. Oxygen is 1, 2, 3, 4, 5, 6 valence electrons. And so I'm going to show that these become those lone pairs structural drawings. They're already partnered up. And oxygen will choose to gain 2 in order to fill those 2 sides up. And so when it does that, it would look like this with all of them full, brackets, and a charge. All right, so basically your end drawing for these anions or cations will either have where it has 4 lines or 0 lines around it, okay, depending whether it's a positive or a negative charge. All right, noble gases, why do they not have a charge? Well, looking at its structural, let's say we talk about neon. Neon has 8 valence electrons, okay? And so therefore all of these would be full already, so you wouldn't have a spot to fill it in. So that would be neon normally, and there would be no brackets or charge ever written for neon because they are completely full as it is originally. All right, so depending on what type of elements you're combining, you're either going to have an ionic or a covalent compound. Those are the 2 biggies in this class, okay? So ionic compounds are formed when electrons are transferred, so it's a give and take of electrons. They are combined, they are formed by metals and nonmetals. How do you identify an ionic compound? You look at the very first element. If it is a metal, it is going to be an ionic compound. Okay, and the properties. Because it is a transfer of electrons, they're not sharing them. It is a total, hey, you take all of my electrons, I want to lose them up. It's a very, very strong type of bond because everybody's exactly how they want to be. It's extremely strong, which means you're going to have a high melting and boiling point. They're going to be great conductors of electricity. Why are they going to be good conductors of electricity? Because in order to conduct electricity, if you look at the word electricity, you see the word electron in it, and that's how you get it is electricity is the movement of electrons. And because these guys are moving and they have these positive and negative charges, these electrons are moving, they're going to be really good conductors of electricity. And they tend to form crystalline solids. So when you think of like salt as being a perfect little cube, okay, salt cube, that's what it is. It forms these perfect little crystalline solids. Salt is an ionic compound, and that's why that is a really bad cube. I'm sorry about that, but it should be a perfect little cube. So the other type of bond that we're going to be talking about primarily is molecular or covalent compounds. I'm going to let you know I tend to call them covalent, but if you ever see the word molecular, understand that they are the exact same things. And how do you form that? Well, instead of giving and taking electrons, these are when electrons are shared. okay, between them. So look at that co prefix with, which means with and share and work, together. That's what happens is you got this covalent compound. So you're sharing, these valent, which means valence electrons. Okay, how do you get these? They are combined when they're made when you have two nonmetals that combine. We're not going to be talking about metals combining with other metals in this class, so don't worry about that combination. Because you are sharing these electrons as opposed to the give and take, these guys are not as happy, I guess you would say, as far as the individual elements go. And because of that, they have low melting and boiling points. They're poor conductors of electricity because we don't have that movement of electrons. There is no movement of that. Okay, so therefore they are bad conductors of electricity because these electrons are not able to move. And you can see them in various states of matter. You have solids, you have liquids, and you have gases and appearances. So like an example for a solid would be sugar. Okay, for a liquid, you're talking about water. And for a gas, you're talking about carbon dioxide. So these are all have covalent compounds. They are all covalent compounds, but they have extremely different appearances. Whereas ionic compounds, because they have that extremely high melting point, they are almost all solids at room temperature. All right, so let's explain why these are the way they are. So it all goes back to their valence electrons in that Lewis dot structure. So we're going to talk about NaCl. Okay, I'm going to do Na combining with Cl. So Na traditionally has one valence electron. Chlorine has 7, so it's going to look like this. Okay. So now what's going to happen is chlorine will want to gain only one electron. Sodium will want to lose it. So how do you draw the Lewis dot structure of this occurring? You'll have sodium donating its extra electron to the open spot. So now sodium is happy. So when it's happy, you draw it to the side, give it its brackets, and give it its charge. Cl is now happy, so you put it to the side, draw what it currently has, which is 8 valence electrons, and give it its charge, which is -1. So now that everybody's happy, you have your total compound. So when I combine with Na with Cl, my formula will be Na. How many Nas did I use to make this? I used 1, so Na1, Cl, and how many did I use to do that? 1. Okay, now we tend to not write those 1, so you would condense it to NaCl. So that's how we get sodium chloride. All right, now we're going to combine Ca with Cl. So what would its structure be, and why does it occur that way? So we've got Ca. Ca tends to have 2 valence electrons, and Cl has 7. So it would look like this. Okay, so Ca is going to want to give up 2 electrons. Cl is only going to want to accept 1. So this Ca is going to donate 1 electron to that guy. Ca at this point has only lost 1, so therefore it is not happy. But the Cl has gained 1, so it is extremely happy. So you draw it to its side. It now has its full octet. It is done. Give it its charge, and you are done with that guy. The problem is that Cl is not happy. So what happens? Another Cl will come in, and this Cl will also have 7 valence electrons. So now the Ca will donate its other valence electron. So Ca is now happy. Give it its charge, which means it lost 2 electrons total, and so now it's happy. And now this Cl is actually happy. So it would have now 8 valence electrons. Give it its brackets, give it its charge of -1. So now what you want to do to come up with the formula is you're going to figure out how many Cas did I use. So just look at your brackets. How many things do you have in brackets? I have 1. So it's Ca1. And then how many Cl's do I have? 1, 2. So I'd have Cl subscript of 2. Okay, and these are ionic compounds because you have that give and take of electrons. So whenever you see those arrows, that shows that you have an ionic compound. Okay, let's try MgN. So we have Mg, it has 2 valence electrons, N has 5. Okay, so Mg is going to donate 1 here, and let's say 1 here. So this Mg is entirely happy. It has no more to give up, brackets, charge. This N, on the other hand, is not happy. So what's going to happen is another Mg is going to come around, and it's going to be like, hey, I'll donate some. So it's got 2. It's going to donate 1 to that N. And now Mg's like, hey, I'm not happy. But N's like, peace, I'm happy. So it goes away. Okay? So now it has that 8. And it gained a total of 3, so it's got a -3 charge. And Mg's like, hey, wait, I want some more. I want to give away that other extra electron. So another N comes by and says, hey, I've got 5. I want 3 more. Can somebody help me out? And MG's like, sure, I can help you out. So it donates that little N there. Okay. And now MG's like, peace. I'm happy. So it goes to the side and it's like, hey, I lost my 2 valence electrons. I'm out. And then this N's like, wait, I'm not happy now. So another MG is like, well, I'm not happy either. So it comes by, it's got its 2 valence electrons. It's going to donate its 2 to N. And now this MG is happy. So it's got MG and it's got its +2. And then now this N is happy because it gained its 3. So it's got its brackets charge, all of its valence electrons accounted for with that -3 charge. And so now what we're going to do is we're going to write the formula. So when Mg ever combines with N, it combines with 1, 2, 3 Mgs. So it's Mg subscript 3. And then N, we have 2. So N subscript 2. So what happens with covalent compounds? Well, when we combine carbon with oxygen, we have carbon has 4, and it wants to tend, for when we're combining with another nonmetal, it's going to want to gain or share the electrons. So in the other case, oxygen, which has 6, okay, and we'll go more into the covalent. We have a whole unit once again next semester over why these share. But what I want you to understand is that they are sharing those electrons as opposed to giving and taking right now. So carbon wants to gain 4. Oxygen wants to gain 2. So the problem is that they both want to gain. So what they end up saying is, hey, let's create a deal and let's both share these. So what happens is that they share these electrons. So what this oxygen is like, hey, I now have my 2 from that guy and my 2 from that guy, and I'm happy. And then carbon's like, hey, I've got 2 from this guy here and 2 from this guy here, so I'm happy on that end. And if I could just bond with somebody else right here, now I've got my lovely 8 electrons being shared. So how this ends up looking in reality is you've got your carbon. Okay, each time you have these lovely loops, and we'll once again emphasize, I don't expect you to be able to draw these right now. But I do expect you to understand once I draw final structure that it would have a covalent compound. And the reason why is because they're sharing these electrons. Whenever you have a sharing or these circles, you draw 2 lines in between because I have 2 circles. Okay, and then we've got an oxygen, it has those. And then we've got these 2 circles on this side. Okay, and it's going to be sharing those electrons. So anytime you have these lines in between 2 elements like this, they are sharing those electrons. So if I count how many electrons oxygen now has, we have 2, 4, 6, 8. Now it's not all at the same time at that one oxygen, but it's cool enough with it. And then carbon has 2, 4, 6, 8. And this oxygen on the left has 2, 4, 6, 8. So everybody's happy in this case. All right. Now if you look at CF4, okay, C once again wants 4. Okay, it wants to gain 4. F wants to gain 1. So what they do is they create a compromise. And they say, hey, if we share our electrons, our valence electrons, where we're all sharing them so we can kind of pretend like we've got those 8, we'll all be happy. So our final structure for this guy would look like this. Notice that we don't have any charges. Notice that we don't have any of the arrows in our final structure for covalent compounds. And the reason why is because these guys right here these electrons are being shared, which is the quintessential part of covalent compounds.